All right, well, welcome to May. Um, Let me just go ahead and get this out of the way. Happy Star Wars Day. For those of you who don't get it, that's all right, but happy Star Wars Day. I am wearing my I Am Your Father Darth Vader t-shirt because it is Star Wars Day. But anyway, welcome to May. We're cruising right along, and I hope you guys are kind of getting the feel for this trig stuff. But we're just about ready to turn down a different path. We're going to go ahead and talk a little more about inverse trig functions today, but then after that, we're going to start doing the algebra with the trig. So it's kind of another chunk of trig class. So get ready for your algebra. Start boning up on things like factoring and adding fractions and all that good stuff, because we're going to be doing it. And then making use of identities to help us simplify stuff. But that's where we're going. But I do want to talk a little bit today, show you some more examples of the inverse trig functions and how they work, because we're not quite done with that. And I want to make sure I show you a few more things before we jump into chapter 9. So before I go there, any questions on the homeworks? Homework's doing all right? Okay, so again, I will take silence as things are going fine. Thanks for that thumbs up there, Diego. All right, well, let's talk inverse trig functions again. So let's go to the board and let me remind you some of what we did last time. So the idea with inverse trig functions is that we want to be able to go the opposite direction. We want to start with a trig function value and figure out what the angle was or is that gives us that. And so what we ended up having to do, though, was restrict the trig functions to make them one-to-one. So you may remember that for inverses, you need a one-to-one function. And the problem is that none of the trig functions are one-to-one. So what we did was we just kind of, well, we did the typical mathematician thing, which was let's ignore the pieces that make it not one-to-one so that it actually is. So for example, with the sine, right, where we had f of theta equals sine of theta, we actually restricted it. And does anybody remember the restriction on theta for inverse sine? What bit we actually allowed for sine? You can either yell it out or type it in the chat window if you remember. All right, so Diego, yes, it is exactly minus pi over 2 to pi over 2. So we had to restrict, and this interval made it so that we only got every value from sine once. And we had lots of different options, but the reason we chose this interval is because it contained the first quadrant, angles between 0 and pi over 2. So that was the restriction we put on cosine, or sorry, for sine. For cosine, it was similar. That was the first one we did. And that one we were actually able to restrict it to 0 to pi. And that gave us all the values exactly once. And then for tangent, we had to restrict it again, but we just went minus pi over 2 to pi over 2. But this has parentheses instead of brackets. So it's a little bit different than sine. It's very similar. But the parentheses, those are there because tangent's not actually defined at minus pi over 2 and pi over 2, whereas sine was defined everywhere. So we put those restrictions on the domains so that they are now one-to-one, which then led to our inverse trig functions. And so now we've got sine inverse. And so if we call this guy, let me call it different, call it E, if they equal sine inverse. So this one, its domain were numbers between minus and 1, or minus 1 and 1. So those were the values that we got out of sine. And then the range Well, that was that restriction that we had to put on sine of theta to make it actually be 1-to-1. So that's how sine inverse works. We plug in numbers between -1 and 1, and we get angles between -π/2 and π/2. So then cosine is similar. We'll call that guy Q. We'll call this guy cosine inverse. Again, its domain is also -1 to 1, but its range is that other restriction, which was 0 to pi. So again, put any number you want between -1 and 1, and cosine inverse is going to spit out an angle somewhere between 0 and pi. And then lastly, tangent. We look at tangent inverse. Call that guy, say, r of theta. So tangent inverse. And what we saw for this one in terms of domain and range, its domain was all real numbers, because we get all real numbers out of tangent. And then its range was, again, just -π/2 to π/2, which was that restriction that we had to put on tangent to make it 1-to-1. So you can plug any number you want into inverse tangent, but it's only going to give you an angle somewhere between -π/2 and π/2. Oh, and maybe you noticed, I can't tell if you can tell, but I do have different colors now. So I'm going to be playing around with them. Let me know if ever there's a color that I put up that you can't really see very well, and I'll make sure that we don't use it. I'm going to try to just go with darker ones, but this should make it a little less boring. Anyway, so those are inverse trig functions. So this is how it works. For example, if we do, say, sine inverse of 1, what's that going to give us? What's the inverse sine of 1? All right, so it's kind of silent out there, so maybe you're having a little bit of trouble thinking about this. Again, this is what this means. We're looking for an angle whose sine is 1. So basically, this is the same question as what angle gives us a sine of 1. So Bella just put up on the chat π/2, and that is exactly what we're going to get, because that's the angle that's in the range of inverse sine, whose sine value is equal to 1. So this is literally just going backwards on our chart. Like, you think about our chart when we built it, we put our angle on the left and then our trig value on the right. Now we're going the opposite direction. So think about looking down that list, looking down the sine or cosine or whatever, and then figuring out where that value is and which angle it'll be. Okay, so there's sine inverse of 1. How about if we do cosine inverse? Let's try cosine inverse of -1/2. Okay, so there's another one. So what we're looking for is an angle whose cosine is -1/2. So go down your list, find me an angle who gives a cosine of -1/2. Just make sure that angle is somewhere between 0 and pi. So what number is that? All right, so Mariola just said 2π/3, and that's exactly right. We know that the cosine of 2π/3 is -1/2, and it is the angle that's in the right interval for inverse cosine. All right, so one more for inverse tangent, just to be complete here. Let's say we've got inverse tangent of -1. So again, inverse tangent, we can have any number. We can plug any number we want in. So I'm plugging in -1. But we're looking for an angle whose tangent is equal to -1. So what's this one going to give us? All right, so Mariel just put 7 pi over 4. You guys good with that? Because that's definitely on our chart, right? 7 pi over 4 gives us a tangent of -1. But is it the one that inverse tangent's going to give? Okay, yeah, Diego just put it's not in the range. And that's true. This guy, 7 pi over 4, it's actually not in this interval, the restricted interval for inverse tangent. It's too big. 7 pi over 4 is more than pi over 2. But Mariola, you're close. Okay, so now you just put 3 pi over 4. Now 3 pi over 4 is also another place where inverse tangent, or where tangent is -1. Is 3 pi over 4 in this interval? Let me give you a tip for the fractions, because I know sometimes it's hard for people to think, okay, is 3 pi over 4 bigger than pi over 2, smaller than pi over 2? Forget about the pi's. Just forget about the pi's and look at just the fractions. Okay, because if you look at the fractions, this is 1/2. And then if you think about like 3 pi over 4, that's 3/4. And so we know 3/4 is bigger than 1/2, which means 3/4 pi is going to be bigger than pi over 2. So unfortunately, 3 pi over 4 won't work either. So then I see Bella just put up, how about minus pi over 4? Minus pi over 4 is the angle that we're going to get from the inverse tangent of -1. It's now in this interval. -1/4 is between -1/2 and +1/2. And it still gives us an inverse tangent of -1. So sometimes it's a little tricky to figure it out because the angles that we have on our chart aren't necessarily the ones in the interval that are going to apply. And that's specifically true with tangent and sine. So here's the trick for tangent and sine, and I shared this last time, but I want to remind you that the way to do this, if you've got a negative inside of a tangent or a sine, this is only tangent and sine. But if you've got a negative in there, just think about what it would be if it was positive. Because this one, if it had been a positive one, the inverse tangent of +1 would be just plain old pi over 4. We know that if it's a positive number, it's always going to be from the first quadrant. So you can just find the one that's in the first quadrant. But notice what happened. If we change the inside from positive to negative, the angle also changed from positive to negative. And that's going to be true with sine as well. And that's because of the fact that they're odd functions, sine and tangent. So that's a little tip just from me to you. If you're ever doing the inverse tangent or inverse sine of a negative, pretend like it's positive, and then just throw a minus sign. All right, so hopefully this is a good little review of how these guys work and what we're doing with them. But what we need to work on a little bit more today is composition. So I showed you composing when they were the same function. So when it was like sine of sine inverse or cosine inverse of cosine, things like that. And what's really nice is that when they are the same, so for example, if we have sine inverse of sine of x, this is gonna equal x as long as x is in the domain of sine. Okay, that's the important thing here, is that x is in the domain of the inner function. So basically this one, we're just going to get x anytime x is between minus pi over 2 and pi over 2. And that I should put here in the domain, I'm going to put restricted. And the same thing is going to be true if it's cosine inverse of cosine. And also tangent inverse of tangent. And similarly for the others, the non-big three. But every time these things, if we compose them, we're going to just get out x if it's in the restricted domain. And where it gets interesting, though, is when we're not in the restricted domain. So let me remind you about how that works as well. So here's an easy one. Let's say we've got sine inverse of sine of pi over 3. So we would look at this and go, all right, pi over 3, it is in the restricted domain for sine, because it is between minus pi over 2 and plus pi over 2. So those things are just going to cancel each other out, and I'm left with pi over 3. Similarly, if I did, say, tangent inverse of tangent of minus pi over 10, minus pi over 10 is in the restricted interval for tangent. It is between minus 1/2 and plus 1/2 pi. So those things cancel each other out, and boom, that's just minus pi over 10. So these are the easy ones. These are the easy ones because we're in the restricted domain. But if we're not in the restricted domain, then we have to get a little creative. So let me show you one with cosine. So let's do cosine inverse of cosine of, let's go, 17 pi over 9. And I specifically gave you an angle that we don't know about. So we don't know the value of cosine of 17 pi over 9. But it turns out we don't need to know that in order to solve this. All right, so here's how we have to get creative. So 17 pi over 9, first of all, notice that that is not in the interval for cosine. It's not in that restricted interval, because for cosine it has to be between 0 and pi, and this is more than 1 pi. Since the numerator is bigger than the denominator, it's more than 1. Okay, so here's what we have to do. We actually have to think about where else do we get the same cosine value? What other angles give us the same cosine value? And then we just have to figure out which one of those will be between 0 and pi. All right, so here's my recommendation with this. Draw a picture. Start by drawing a picture. So let's figure out where 17 pi over 9 is. Can you tell me what quadrant that's in? And you got a 1 out of 4 shot. All right, so I got a couple people that are typing in 4, and that's perfect. It is in the 4th quadrant. Again, think of it as a fraction. 17/9, that's 1 8/9, which is just slightly less than 2. So this angle is somewhere down here. So there's 17 pi over 9. All right, now, again, that's not in the right interval. So let's see if we can find one that is. So the first thing I think about is, where do I have to be for inverse cosine? Which quadrants am I allowed to have for the restriction on cosine? So we know we have to be between 0 and pi. So the 0 is over here, and of course pi is pointing in the negative x direction. So I have to be somewhere in the first or second quadrant. So this angle won't work, nor will any that are coterminal to it. If I found that I was actually in the right place, then I would just add or subtract 2 pi until I got to the right angle that I needed. But I don't have that here. I'm in the wrong location. So here's how we have to think. Start with plus or minus. Is cosine plus or minus down here? Is cosine positive or negative in quadrant 4? All right, so I got a couple of people chiming in with positive. Good, so it's positive, which means I need to find an angle in the first or second quadrant that's also positive, which of course means I need the one in the first quadrant, because the first quadrant, everything is positive. So really what I'm looking for then is, what is this angle that's got the same symmetry? Well, you may remember this as a reference angle. The reference angle is a first quadrant angle that has the same symmetry as your given angle. So in the case of positives, we're always looking for the first quadrant angle, so it's going to be the reference angle. All right, so what is that reference angle? How far are we rotating there? So since people aren't chiming in right away, I'm thinking maybe that means we're still not confident on finding reference angles. In the fourth quadrant, the reference angle is just how far away we are from one complete cycle. So we just need to know how far are we from getting to 2 pi. So what we can do is just take 2 pi minus 17 pi over 9. So in the fourth quadrant, it was always 2 pi minus theta, or if we're in degrees, 360 degrees minus theta. But we'll do 2 pi minus theta. So 2 minus 17/9 is 1/9. And I saw that William had put in there that he saw pi over 9, and that's exactly right. So the reference angle for that is pi over 9, which means that's the first quadrant angle that has the same cosine value. And that's actually what we're going to get if we do cosine inverse of cosine of 17 pi over 9. So these do get challenging, especially when we're not in the correct interval, but that happens. When that happens, we just have to find the right place. All right. Well, that's these guys when we're dealing with the same trig functions, but we don't necessarily have to have the same trig functions, right? We can have things like this one. So I'm going to compose again, but this time I'm going to do what's called mixed composition, because I'm going to have different trig function than the inverse trig function. And let's start with this. Let's say that we've got the sine of the cosine inverse of 13/12. No, let's go either. Go 1/2. All right, now had this been, say, sine of sine inverse of 1/2 or cosine of cosine inverse of 1/2, the answer would be 1/2, and we'd be done. Unfortunately, that is not the case. So the question is, how do we do this one? Well, let's just treat these as individual functions and think about what we would do to do them individually, right? Like this is saying, let's start with the cosine inverse of 1/2. So I gave you an angle that you know. What is cosine inverse of 1/2 going to be? What angle will that give us? All right, so Diego just threw up there pi over 3, which is exactly right. This is the same as pi over 3 because the cosine of pi over 3 is equal to 1/2. All right, so that means that this is the same then as sine of pi over 3, which again is an angle that we know. We can look at our chart, or maybe you've got it memorized by now, but that's going to give us the square root of 3 over 2. So that tells me then that the sine of the cosine inverse of 1/2 is going to equal the square root of 3 over 2. So notice that all I did was I made use of the fact that I could find the angle in here, right? Like really what I'm saying here, when we write cosine inverse of 1/2, that's an angle, right? That's just saying, hey, find me the angle whose cosine is 1/2, and then put that angle into sine. So that's really what's going on when we're doing this composition. Like this first one just says, hey, find me this angle. And then once you've got that angle, put it into sine and see what happens, right? And that's what we did here. We figured out that the angle that gives us, or that cosine inverse of 1/2 gives us is pi over 3. We then took pi over 3 and put that into sine, and we got our number. So it's not really any different than other compositions. We just kind of have to follow along and see where we're going. So we just take the next step. But, that's what we did here. All right, so hopefully no big deal. Kind of see what's going on. Thumbs up. If you're still a little confused, maybe give me the clappy clappy. All right, I'm getting lots of thumbs up. Cool. All right, now I was kind of nice and gave us an angle that we already knew. So I'm going to change this just ever so slightly. So we just did sine of cosine inverse of 1/2. This time, let's do sine of cosine inverse of 12/13. So don't bother looking at your chart because you're not going to find it. You're not going to find an angle whose cosine is 12/13. We don't have that. All right, so what do we do now then? Well, what we do now is we still kind of follow the same deal, right? Like think about what we did before. We were saying that the inside of this, the cosine inverse of 12/13, that's some angle. I just don't know what it is right now. But what I do know about it is I know that its cosine is 12/13. And I know that because that's what this says, right? Cosine inverse of 12/13 is saying find an angle whose cosine is 12/13. And still, what I'd really like to know is, what is the sine of theta? So it's exactly the same thing as we did last time, except this time we don't know this angle, but we do know its cosine value. All right, so the question is, where do we go from here? How do we figure out what the sine of that angle is? Anyone have an idea? Okay, so Bella just said that cosine is x over r, and then Diego throws in Pythagorean. Yeah, I love it. Both of you guys are seeing kind of the two different approaches, but regardless, go back. You may remember back in the first chapter we did, the old, here is a trig function, find the rest. You may remember there was a question on your exam like that. Well, that's what this is saying. Here is a trig function, but instead of finding the rest, we only have to find one other one. So we definitely have some choices. Let's start with the idea of using the Pythagorean. We know the relationship between sine and cosine, right? We know sine squared plus cosine squared is equal to 1. So since we know cosine, we can put that in here. And we can find the sine by solving this. So real quick, Yair, you just said, why isn't cosine negative if it's inverse cosine? Okay, so inverse cosine, all that's telling us is we're going backwards. And what sign we use is the sign that's on the numbers in here. So this was 12/13, which means it's going to be 12/13 always. This -1 doesn't actually change the sign. It's just telling us we're going backwards. That's what you need to think when you see this. Is go, oh, okay, find an angle whose cosine is this number. So does that make sense? Yep, okay, good. All right, well, let's continue solving this real fast. So we're going to get sine squared plus 144 over 169 equals 1. If we subtract that over, we're going to get sine squared equals 25 over 169, which then means I take a square root. And since I took a square root, I'm going to put a plus or minus. But we've got that the sine of theta is equal to plus or minus 5/13. All right, well, so we know this at least up to its sine. It's either going to be 5/13 or it's going to be minus 5/13, but it has to be one of them. I can't have an or. So do you remember how we dealt with this back in the day when we were doing this? How did we decide whether it was plus or minus? All right, is that a we don't remember? There you go. So Adam just said we need to figure out the quadrant that it's in. And that's exactly right. If we know what quadrants it's in, the angle is in, then we know which value, plus or minus, to attach. Okay, so where is theta? Which quadrant is theta in? And again, you got a 1 out of 4 shot, even if you just guess. So what quadrant is this angle in? All right, so let's see. Adam guessed 2, William guessed 4. Diego gives me 1. All right, cool. Anyone want to give me 3 just to round it out? No, I'm starting to get more 1s. And that's right. It is quadrant number 1. And I know what you're thinking. So now you're like, okay, so great. How the hell do I know that it's quadrant number 1? Right? It seems kind of random, but it's not. Check this out. So first of all, we know that cosine is positive. Cosine being positive, there are only 2 places where that can happen. That's either quadrant 1 or quadrant 2. So just from this, the fact that this is positive, tells me that this is quadrant 1 or 2, right? Because it's positive. So already we've restricted ourselves down to either first or second quadrant. Okay, so then Bella said because they are both positive, and when you're saying both, do you mean the 12 and the 13?
Mm-hmm. I think just the sine and the cosine, right?
Okay, well, so we know the cosine is positive, but that's the thing is we're trying to find out whether the sine should be positive or negative. And so unfortunately, just the 12/13 isn't enough to tell us about the sine. It does tell us though that we're in either quadrant 1 or 2.
Can't you just divide by pi and figure out the ratio of pi left? And then if it's, I mean, it comes out to like 0.29. So you know it's less than 1/2 pi. So you know it's in quadrant 1.
Okay, except this isn't an angle, right?
Radians.
Okay, so that would be the first quadrant angle though, because there's also a second quadrant angle that will give us 12/13.
Okay.
So, but here's the trick. It's the restriction. Remember, with these inverse trig functions, we're restricted to where we can be. The very first thing we did was we calculated an inverse cosine. Inverse cosine doesn't just give us random angles. It's going to give us angles that are trapped between 0 and pi. So, oh, you know what? I totally lied here. This is quadrant 1 or 4. Sorry about that. Cosine is positive in quadrants 1 and 4. I was thinking the next step ahead. So inverse cosine, this guy, so the inverse cosine bit, that tells me that I'm in quadrant 1 or 2. Because that's the restriction for inverse cosine. We can only have angles between 0 and pi. All right, so here's how you do this. Inverse cosine, I'm in quadrant 1 or 2. Positive means I'm in quadrant 1 or 4. Since I have to be in the same place for both of them, that tells me that I'm in quadrant number 1. So this is how you can actually figure out what quadrant you're in, is by looking at the two pieces. The first is, do we have a plus or minus on the inside? So use that to figure out which two quadrants we can be in for that trig function. And then look at the inverse trig function restriction, and that'll tell us where we are. All right, so very long story short, this is going to end up being positive 5/13 because in the first quadrant, sine is positive. So we can erase that plus or minus and just make it plus. So the sine of the cosine inverse of 12/13 is 5/13. Okay, so I have this magic ability. Just hold on a second here. I want to look at you guys for a second. So I have this magical ability. I have the power to actually look through your webcams, even though you've got it blocked from video. And I can see all of your faces right now. And a lot of them are, what? Let me do another example and we'll kind of walk through this and you'll see what the process is, because I know that there was a lot here and it's kind of a little crazy. So let me go back and walk through and show you one more time. Oh, and by the way, that's a joke. I totally can't see any of you. As far as I know, nobody's even there. But anyway, so let's go back. Let's do another one and we'll walk through the process. But remember, we're looking for two things. One, what does the sign, the plus or minus sign, tell us? Right? And then two, what does the inverse trig function tell us in terms of the restriction? And we use those two together to figure out where we are. All right, so yeah, Kiva, go ahead, take your sticker off the camera. No worries. Well, at least from me. You might still want to keep it from all the hackers coming in from other places. All right. So let's try another one here. Let's do the cosine of the inverse tangent of minus 2/3. So cosine of inverse tangent of minus 2/3. So let's start with what we know. So the inside here, again, remember this is an angle. And what we know about this angle is that that the tangent is minus 2/3. And so then what we're looking for is, what is the cosine? So this is, I just gave you tangent. Now you tell me cosine. So let's start by figuring out what quadrant we're in. So tangent being negative, there are two choices from this. And this is either quadrant 2 or quadrant 4. That's where tangent is negative. So we're in one of those two quadrants. But we definitely need to know which one, because cosine, its value will change depending upon which one we're in, right? In quadrant 2, it'll be negative. In quadrant 4, it'll be positive. Okay, so that's what the sign, the plus or minus sign, tells us. But then let's use the inverse trig function and think about what it tells us. So we're looking at inverse tangent. So what quadrants does inverse tangent give? What does the restriction on inverse tangent tell us in terms of where that angle is? I'll do the easy part. It's quadrant 1 or somewhere else. What's the other quadrant for inverse tangent? All right, so I got a whole bunch of people telling me 3. Unfortunately, that's not correct. Think about the restriction that we had to put in place for tangent to make the inverse work. It's from minus pi over 2 to pi over 2. Does that help you? Which other quadrant? So Diego just put up 4. So Bella says she thinks 2. Well, for this one, it's 1 or 4. 1 or 4. Let me draw you a picture here. This will help you see it maybe. So think cosine, for example. Cosine, we were between 0 and pi. Okay, so this purple is the cosine. For sine, we were between minus pi over 2 and pi over 2. So here's minus pi over 2 up to pi over 2. So there's sine. But that was actually also the same for tangent. Sine and tangent had the same restrictions. So visually, this is those intervals for the restriction on these three. So cosine was between 0 and pi. Sine and tangent are between minus pi over 2 and pi over 2. So that means cosine inverse is always going to give either quadrant 1 or 2. And sine inverse and tangent inverse are going to give 1 and 4. So that's how I knew from the inverse tangent that I was in quadrants 1 or 4. Now, if I combine that with the fact that tangent was negative, tells me exactly where we need to be. We're going to be in quadrant 4. So there's our two-step process again. Start with the sine value, the plus or minus from our number. And then look at the inverse trig function, and between those two, we can figure out exactly where we are. Okay, so we are in quadrant 4. So we're down here. And do you remember why we did that? What was the whole point of doing that? And it wasn't just for the hell of it. Remember why we cared about where we are? Good, yeah, Mariola. It's the plus or minus of cosine. So what's the sign of this going to be? Is it going to be plus or is it going to be minus? So what's the answer to that? Is this one going to be plus or minus? Good, it's going to be plus. So I'm going to go ahead and put that right here. So this is going to be a positive. I know we don't usually put a plus sign before a number, but this way I'll remember when I get there that I've actually got for sure the value. All right, so now I have to find cosine given this tangent. So we could use the identities. Again, what we'd probably want to use is the Pythagorean identity that involves tangent and secant. Let me just show you how that would play out. The one that involves tangent and secant is tangent squared plus 1 equals secant squared. So we'd have minus 2/3 squared plus 1 equals secant squared. So that's 4/9 plus 1, which if I get a common denominator is 13/9. So then to get the secant, I would take the square root. So I get secant of theta is the square root of 13/3. And again, it's plus because we know we're in the fourth quadrant. So then to get cosine, I just got to flip it over. And we would get 3 over the square root of 13, which if you felt so inclined, you could rationalize. All right, so using the identities, we can get there, and we now have the cosine of the tangent inverse of minus 2/3. We know that's equal to 3 over root 13. All right, but I want to show you another way. I want to show you another way that we could have figured out the cosine value that didn't use the identities, because I know right now the identities are probably still a little confusing. You may not have them down well. And it's a lot of algebra. And a lot of us don't like algebra. So let me show you another approach using a right triangle. Okay, so I'm going to do another thing here real quick, where I'm going to draw a right triangle. Now, this triangle is not in the fourth quadrant. Okay, so whatever this angle is that I'm drawing, it's not the one that's in the fourth quadrant, but it's the reference angle. Okay, it's the reference angle for that. Now, here's what I know about it. I know that its tangent is 2/3, which if I use the good old SOHCAHTOA, tells me that those two sides, the opposite over hypotenuse are equal to, or sorry, opposite over adjacent are equal to 2/3. So I'll just put those in as 2 and 3. Now, once I have those two sides, I can find my third side using the Pythagorean theorem. So 3 squared plus 2 squared, that's 13. So this is the square root of 13. And now if I want cosine, cosine is adjacent over hypotenuse, which is 3 over root 13. And again, with that magical ability, I can see a lot of you nodding your heads and smiling because you like this a little bit better. And that's cool. I definitely like this better as well. I think it's a lot faster. But we still have to pay attention to what quadrant we're in, because we lose that information when we draw a right triangle. Remember, in a right triangle, we're saying that this angle is between 0 and pi over 2, which may not actually be the case. But it's faster. We still have to pay attention to where we are. But this is my preferred method. But don't forget about identities. Identities are useful. All right, so I just want to show you one more example before we turn our attention to something else. And this time, I want to throw in some letters. Okay, so here's what I'm talking about. Let's say we're going to compose and do this. We're going to do tangent of sine inverse of 1 over x. So now we don't actually have a number there. Think of it this way. We just want to maybe allow ourselves this form. So you can give me different x's and I can still figure this out. And mathematicians, again, remember I told you we're lazy. We're going to do this one time. We're going to get a formula that involves x so that we never have to do it again. So if we ever get into this kind of form, we know exactly what to do. Well, if we kind of break this down like before, this is basically telling us we know that the sine is equal to 1 over x. And we want to know then, what is the tangent equal? So we could use identities. I'm not gonna. Or we could use the triangle. So let's do the triangle, and let's see what this gives us as our tangent. All right, so here's our generic triangle. We know that the sine of this angle is equal to 1 over x. So what I'm going to do is I'm just going to go with the ratio of the sides. Sine is opposite over hypotenuse, so I'll make my opposite side 1 and my hypotenuse x. All right, so if I want to find the third side, we're going to use the Pythagorean Theorem. I'll just call it A for right now. I know that a squared plus 1 squared is equal to x squared. So a squared is equal to x squared minus 1. So a is the square root of x squared minus 1. Now, if I want to be really good about it, I do need to put a plus or minus on that, because I don't know if it's positive or negative. It'll depend on where we are when we eventually get there. But let's go ahead and find the tangent. So tangent is opposite over adjacent. And so what that gives me is 1 over the square root of x squared minus 1. And there you go. Anything of this form, tangent of sine inverse, 1 over x, it's just going to equal 1 over the square root of x squared minus 1. Again, plus or minus, it depends on the x value. If x is positive, this is a first quadrant angle, so I'll get a positive value there. If x is negative, then this is a fourth quadrant angle, and now my tangent will be negative. All right, so that's the approach here. And you may be asking yourself, okay, why? Why do we care about this? And you're going to really hate this answer because this is a total dad answer. Oh, you'll see. When you get to calculus next year, you're going to do a ton of this in the stuff we call trig substitution, which is one of the modes for integrating. So right now, I'm going to tell you, remember this, so that in probably around February of next academic year, of next year, I can say, hey, remember when we were in trig and I showed you? I'm going to remind you about this. All right. So anyway, take it for what it is. It's just a way of eliminating the trig functions, right? I mean, in essence, we took these trig functions and instead turned it into an algebraic expression, which is going to make things way easier for us in lots of situations. So Adam, oh, do I teach the full year of calc? No, I don't do the full year. We trade off in terms of what it's going to look like next year. I don't know for sure because things are always fluid. So I don't even know that I'll be the one teaching you second quarter, but I think I'm on tap for it. I do know that I will not be teaching first quarter. Well, as of right now, I'm not teaching first quarter, but a lot of things can change between now and September. All right, so there are your inverse trig functions. Just take them for what they are. So the other teacher, Mariola, Larry Green, is on tap to teach the first quarter. But there might be others. Right now, Larry and I alternate, but I know that Wynn Walker, you guys know Wynn, she kind of wants to get in on this too, so she might be joining. I don't know. Real quick while we're on this topic, us scheduling, we have in mind what we want to do, but things vary all the time and things change constantly. Like I was originally on tap to teach first quarter, but then things had to change to accommodate other changes for people. So just be aware that even what you'll see in a schedule can change before your classes even start. So not that you have a choice when it comes to calculus, but don't always take a class just because of the teacher, because sometimes if you pick because of the teacher, you'll still get hosed because the teacher had to change. So anyway, but yeah, if you guys have questions about what we have planned, I don't mind sharing it with you. Just always take it as it might change. Okay, so we're going to move into the next chapter. We're now moving into chapter 9, I think it is, in our book. And chapter 9 is all about doing algebra with the trig functions. And we're going to be actually developing a lot of identities. So far we have a few, right? We've got Pythagorean, the quotient, the reciprocal, right? We've got some relationships between the trig functions, but we're going to build more, a whole bunch more. That's going to be a lot of our next couple of weeks. But what I want to do today is just kind of remind you about the identities we have and how we can use them to build new identities and actually confirm that identities are actually correct. So this is going to be a lot of algebra combined with trig. So if your algebra skills are a little weak, I'm going to give you some ideas of things to practice and go back and look at, because there are some algebra techniques that continually come up that you're going to want. Okay, so let's go to the board real quick, because I want to remind you about the identities that we have so far. So we really have 3 sets. So the first set are the reciprocal. And the reciprocal, those are the basic ones that allowed us to get from the big 3 to the other 3. right? Basically the fact that secant is equal to 1 over cosine, cosecant is equal to 1 over sine, and cotangent is 1 over tangent. So when I mention the reciprocal identities, those are the ones that I'm talking about. By this point, I'm going to guess that you're pretty comfortable with those because we use them all the time, right? Those tend not to be a big deal for people in general. Okay, then the second set, those are the ones we call the quotient identities. And these related tangent and cotangent back to sine and cosine. So we have tangent is equal to sine over cosine. And then cotangent is obviously just the reciprocal of that. So you flip it over. Cotangent is cosine over sine. So that was the second set. And then the third set were the Pythagorean. And the Pythagorean, there were the 3 forms. The one that hopefully you're all kind of getting good with by now is the sine squared plus cosine squared equals 1. We're going to make use of this a lot. And then, of course, there are the other 2 forms that you get by either dividing by cosine squared or by sine squared. And so they're tangent squared plus 1 equals secant squared, or 1 plus cotangent squared equals cosecant squared. So that was the other set of identities that we have. So this is the thing, you want to take a screenshot of this, you want to take a picture of it, you want to reproduce it, you want to sleep with it at night. You want to know everything on this board like the back of your hand, as we say. Okay, so these are extremely important to know. I would say that for the Pythagorean, the least important is the third one that almost is never used. The second one, you can usually get away without it, but it will be useful. We'll also see it in calculus next year. So it'll come up from time to time. The first one of the Pythagorean, definitely no. Definitely no. But it's going to be one that you don't really even have to think about. You're just going to have it down cold. Go ask the calc students in this year or next year's, ask them about which identities they remember. They'll all mention this one. They'll rattle that one off. Okay, so we're going to make use of these to help us actually confirm other identities. All right, so unfortunately, because I've got a small board, I'm going to have to erase this, but we've got it all burned in our brains, right? So here's what we're going to do. We're going to see if we can prove some other identities. So what you'll see in the book and on the homeworks and stuff is they'll call it confirming identities. Which basically means prove them. We're going to show that these identities are actually true. So again, remember what an identity means. An identity is an equation that's true for everything. It doesn't matter what we plug in. It's going to be truth. And so that's what we want to do, is show that these things actually are identities. So let me give you an example of one, and we are going to prove this one in a second, but it looks like this. Sine of theta plus cosine of theta squared plus sine of theta minus cosine of theta squared equals 2. So this is an example of what I'm talking about. This is an identity. If you were to pick your favorite angle and plug it in here, what you're going to end up seeing is that you do get a true statement, no matter which angle you pick. All right, now, what does this mean when we confirm the identity? Well, basically this. What we need to do is we need to start with one side. So pick whichever side of the equation you want to work with. I'll give you some tips on what I do to pick my side, but start with one side. Then we're going to use algebra, identities, etc. to turn it into the same thing as on the other side. So like for this one, we would either pick the left-hand side, the bit that has all this sine and cosine stuff, and then do algebra trig until it eventually turns into a 2. Or alternatively, we can start with 2 and try to turn it into this thing. Okay, so this is the goal with identities. We start with one side and then use algebra, identities, and the like to get us where we need to go. So before we dive in, let me give you some of the algebra steps that are really, really common. Okay, so these are things that you should be good with. If you're not, go back and practice. Okay, but some big things that we're going to see from algebra. First and foremost, factoring. We're going to do a lot of factoring for these. Also, fractions. Know how to add and subtract fractions, build them up, especially when we have variables. Okay, so factoring, fractions, and then another big one we're going to do is FOIL. All right, so a lot of F words when it comes to algebra. In this case, the F words are factoring, fractions, and FOIL. So make sure you know how to do those. I bring up FOIL. I know most people know how to do FOIL, but a lot of times people forget about it and they try to do it a cheaty way. And I'll explain what I mean when we work this example in a second. Okay, so these are some algebra tricks that you definitely need to remember because we're going to use them. There are some other things that I'm going to show you along the way, some trig tricks, another trick I call the miracle step. I'll show you those as we get to them. But let's start just by practicing with these simple ones that primarily are algebra, but we'll see where the trig comes in. Okay, so let's come back to this example, and let's start by picking which side we want to use. All right, so I think this one is pretty obvious that we're going to want to start on the left-hand side. For me, when I talk about which side to pick, what you'll hear me say is that I start with the uglier side. And of course, a word like ugly is subjective because what's ugly to me may not be ugly to you. But I actually like using this word because it is subjective, and often a side I would pick is not the same side you would pick. But I'm going to start with the uglier side. Now, to me, uglier means a couple things. First of all, it means there's more stuff that I can do, right? Like on this left-hand side, there are some pretty obvious things that I can start with. Like, what would you do first? If we pick this left-hand side, what would be your first step to do if you're going to try to somehow turn it into a 2? Any ideas? I know that my first step is actually on the board. Okay, so Bella says, subtract the positive value, move it to the right side. Okay, I don't want to actually move anything from one side to the other. I want to start just with this side and stay only here and do steps. So then Mariola, get rid of the parentheses. And Kiva says exponents. I think you're kind of on the right track there. I want to expand this out. I want to foil. I want to foil these things. Remember, they're F words. This sine of theta plus cosine of theta, this is one of the things I wanted to warn people about. It's really tempting. Don't write this down, by the way, because I'm just going to write it down and then erase it pretty quickly. It's really tempting for people to take this square and just pass it in and say, oh, this is sine squared plus cosine squared. Okay, that is false. That is not true. That is not what this equals. I had a really, he was a dick. I had a professor who was a dick in college who, he made a snide comment all the time. He called this the freshman dream. Because freshmen dream that they could do this, but they're so dumb that they, he was kind of rude about it. But it definitely stuck with me that it is something that we all want to do, but it's something that we shouldn't do because it's not legal. Because what happens here, if we're going to actually deal with that exponent, what we've got is sine of theta plus cosine of theta times itself. Okay, that's what this is, which means we'd actually have to FOIL it. Okay, so it's sometimes hidden. People don't see it as a FOIL, but check out what happens if we FOIL. The first gives us a sine squared. The outside and the inside each give us a sine times a cosine. And then the last gives us a cosine squared. So you can see that we did get sine squared plus cosine squared, but there was more. This is the OI part of FOIL. It's a sine times cosine from the outside, the sine times cosine from the inside, which gives us two of them. So watch out for that. Please don't fall for that. I know you want to. We all want to do that, but it doesn't work that way. So make sure you actually FOIL this thing out. All right, well, that's what we get when we FOIL out the first piece. Let's FOIL out the second piece. So just to save myself a little time and space, imagine that this was a minus sign instead of a plus sign. And let's think about what we're going to get now. Well, we're still going to get another sine squared. So put that here, sine squared. The last is still going to be a cosine squared, because a negative cosine times a negative cosine is a positive cosine squared. And then if we look at the OI part, the outside and the inside, that's going to give us minus sine cosine, which is another minus 2 sine times cosine. So let's add those things together. This now gives me 2 sine squared theta. These sine cosine pieces cancel because I got plus 2 and minus 2 of them. And then I have plus 2 cosine squared theta. So by distributing, getting rid of the parentheses and the exponents, we get to here. All right, so now the question is, what do we do to this to make it look like 2? Because that's where we're going. Use this as the roadmap. My analogy is, I always think about this. This is telling me where I'm trying to go. I'm trying to get to 2. So consult that map. Make sure you're going the right way. Well, how about this? So there's a 2 in both of these. What if I factor it out? So we'll use one of the other F words here. Let's factor out that 2. So we'll get sine squared plus cosine squared. And hopefully you all see it. from the Pythagorean, sine squared plus cosine squared is equal to 1. And 2 times 1 is equal to 2. So we just confirmed this identity. We showed that it is true. We started with one side and one side only, did all kinds of stuff to it until it eventually turned into the other side. Okay, yeah, Bella just said she didn't see the exponents at first. And yeah, if you miss a little bit of this anywhere, you're going to get completely derailed. So be very careful. Pay a lot of attention, go slow. This is one of those places where speed kills. If you go too fast in here, you're bound to make some sort of an algebra mistake, which then will derail you completely. Before we move off of this, I also wanted to show you something. Look at this entire list of everything we did. How much of that was trigonometry? And I don't mean like measuring triangles trigonometry. I mean like trig, we've talked about trig. How much of that was actually trig? Not quite none. And it was a little bit more than just the symbols, but not much more. There was one trig step. It was right here. When we turned that sine squared plus cosine squared into 1, we used the Pythagorean identity, and that was the one and only trig step we did. The rest of it was algebra. So I bring this up to stress how important algebra skills are. Okay, you're going to find this stuff incredibly difficult if your algebra sucks. If that's you, I'm sorry. I am. I'm just trying to be real with you. Just realize that if your algebra skills are weak, these are going to be extremely difficult because the vast majority of what we're going to do are algebra steps. We're going to use trig occasionally when we make use of an identity, but it's going to be rare in the steps of what we do. Yeah. Okay. Well, let me show you another one. We're going to do a few more today, and we'll definitely do some more next time, just because I want you to see how this works and kind of give you some pointers in the different steps that we can take. So before I erase this, any other questions? Okay. So keep it, when you put it in the calculator, it says true. Yes, it should. For an identity, you'll know an identity is true if, like if you just type in an equation, a lot of calculators will either respond with true or false. Unless you say, you know, if you got like a TI-89 and hit solve and stuff, it can do that. But in a case of this, yeah, your calculator should definitely say true. If you were to graph, like put this into your graphing part, you would see that it gives you the horizontal line, y equals 2. So you can also confirm it or check it graphing. But the only way we confirm it is by actually doing the algebra steps. Any other questions?
Yeah, I don't know if this is, I mean, I know there's probably a better reason to actually use this, but isn't this basically just the same formula as sine theta squared plus cosine theta squared equals 1, just with 2's and squares?
No.
Basically, doesn't it reduce to basically the same thing?
Well, it does. It does. But it starts completely different.
So, okay, so there's a different application at one point then. Okay.
Yeah, so in terms of where this is coming from, I mean, I can't tell you for this specific one. Well, where it came from was my head to give us one that was pretty easy to do, just using algebra. But in terms of a real life situation where you're presented with this, I don't know. But the point of identities and kind of what we're doing here is to take something big and gnarly and turn it into something really easy to use. So this isn't just the Pythagorean identity added to itself, because there were these other pieces that just happened to cancel. But you're right, Adam, that it does at least turn into that. So.
Okay, thanks.
Yeah, you're welcome. All right, so let's try another one. Let's look at this guy. So let's say we've got 2 tangent of theta plus secant squared theta is equal to sine squared theta times, in parentheses, secant plus cosecant squared. Barely have enough space to write that on my board. So I've got 2 tangent of theta plus secant squared theta equals sine squared theta times secant plus cosecant, that quantity being squared. All right, so we're going to do the same thing that we did before, which is pick one side only, and try to turn it into the other side. All right, so like I told you, I picked the uglier side, and I like keep it just put in there. Both are ugly. Absolutely, both of those things are ugly. But I definitely see a side that I would pick, and I would pick the right-hand side. Okay, so Mariola agrees with me that the right is uglier. Let me give you a little bit about, or how I decide what's uglier. So first of all, the reason I don't like this right side, 2 things. One, it's got a secant and a cosecant. It's got multiple of the non-big 3, right, of the lesser 3. I don't like the lesser 3. I would much rather not be dealing with secants and cosecants and cotangents. Yes, there's secants on this side as well, but there's only the one, right? The other side I got multiple. And the other thing about the right-hand side is I don't like this, I'm squaring stuff I'm adding together, because that's going to be some kind of FOIL business that we're going to have to do. So I'm going to pick the right-hand side. You can totally pick the left-hand side. It'll work. I'll even show you how you can get from the left-hand side to the right-hand side once we're done. But I'm going to pick the right-hand side because I need somewhere to start. Okay, so in terms of what we can do, so first, if we want, we can FOIL out like we did before. And that's totally good choice here. But I'm going to recommend something else. When you're presented with things that are not the big 3, a very good first step is to turn them into the big 3. Turn them into sines and cosines and tangents. So that's what I'm going to do first. So let me rewrite this then. I'm going to have sine squared times 1 over cosine plus 1 over sine squared. So in a pinch, you can always turn things into sines and cosines and stuff like that, which can make things a little bit easier. Okay, so now the next thing I'm going to do is I'm actually going to add these fractions together. I'm going to combine those fractions into 1 because it'll be easier to square. So this is an algebra step again. So we're going to get sine squared times sine plus cosine over cosine times sine. So this is good old common denominator business. Multiply this first one by sine over sine. Multiply the second one by cosine over cosine to get my common denominator. So that's where the sine plus cosine comes from. That's the tops. And then the bottom is sine times cosine. Okay, so now I'm going to square. So on top, I have to FOIL again. This is actually half of what we did last time. We're going to get sine squared plus 2 sine cosine plus cosine squared. So that's what we get when we file sine plus cosine, or FOIL sine plus cosine. And then on the bottom, we're going to get cosine squared times sine squared. So this one, we can just pull that square in and square each one of them, but that's because we're multiplying. I think this is where the inclination to just bring powers in over addition comes from, is because we can do it with multiplication. All right. So are we ready to start making this look a little bit prettier? Because it's still nasty. But this is where we get to have some fun. So I'm going to crack out my red slashing pen, because I've got a sine squared on top and a sine squared on bottom. But I'm going to cancel. That sine squared out front is being multiplied, so those reduce. And then I'm also going to use the Pythagorean identity. As you see this sine squared, we've got a cosine squared we're adding to it. That's the same as 1. So what this turns into, much nicer now, it's going to be 2 sine theta cosine theta plus 1 over cosine squared. All right. So we're here, but again, this doesn't look like the left-hand side. Remember, what we're trying to get is 2 tangent plus secant squared. So any ideas on what we can do to this to start making it look more like that side? Or if we take the road analogy, the driving analogy, we're completely lost. Like, we know where we're heading, but we still have no idea where we are. Okay, so let's see. So Yair said sine over cosine equals tangent. And then Muriel says multiply by cosine squared. And Adam said reciprocals. Okay, so we got a lot of ideas here. Let me start with the multiply by cosine squared. If I multiply by cosine squared, I have to do it to the top and the bottom, because remember, we're not treating this like an equation. We're starting with just this side. Right? We're only working on the right-hand side. We're only using the left-hand side as our target. So there is no multiply both sides by something. It would have to be top and bottom of the fraction. But multiplying top and bottom of the fraction by cosine squared won't do anything. So we're not going to do that. The reciprocals, I think the idea is, let me see if I'm reading your answer correctly, Adam. Do a little mind reading here. Is the fact that, like, secant, its reciprocal is 1 over cosine. And like tangent, maybe it was sine over cosine. That's where Yair was going.
Yep.
Okay, so what if we do that, but backwards? So here's what I'm going to do. I'm going to split this into 2 pieces. I'm going to make this first one 2 sine theta cosine theta over cosine squared. And then the other piece is going to be 1 over cosine squared. So this is another big trick that is classified under the fractions F word. And that's taking a fraction and splitting it apart, breaking it into the two smaller pieces. Because now, check it out. I'll take my red slashy pen, cancel one of those cosines. So let me rewrite this up here. Again, I apologize for running out of space. But we now have 2 sine theta over cosine theta plus 1 over cosine squared. And I think now you can totally see where this is going to go. The sine over cosine turns into a tangent. And the 1 over cosine turns into a secant. And since it's squared, or it's secant squared. And there you go. We have now confirmed this identity. So there's a lot more to this one. But if you go back and you look in terms of the trig steps, again, it was barely any. We did the first trig step of turning secant and cosecant into sine and cosine. Then we did algebra, 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 till we got here. We did a trig step using the Pythagorean, turn that into 1. Then we did some more algebra, and then our last trig step was at the end to turn it back into what we needed. So again, majority of this was actually algebra, not trig. All right. So if you're feeling a little dejected right now, that's not uncommon. But I'm just going to give you a little, the Bruce pep talk. The more you do these, the more you actually try them on your own and practice them on your own, the better you're going to get. You'll start seeing the patterns. You'll start seeing what the next steps need to be. You'll get there. Real quick before I forget, because I always seem to forget, I want to give you guys the word of the day for today. And in classic Bruce style, it's something that I just grabbed off my desk. Today's word of the day is going to be straw. Straw, as in drinking straw. This was actually used for my physics class as a demonstration, but straw. Okay, so that's the word of the day, straw. All right, well, let's do one more of these, and then we'll call it a day. Let's do another one that requires some algebra. I think it'll be a little bit easier than the one we just did once we get started. But let's try this. Let's go with tangent cubed theta minus 1 over tangent of theta minus 1 equals secant squared theta plus tangent of theta. All right, so we got to pick a side. What do you guys think? Left side or right side? Or at this point, do you even care anymore? All right, I'm seeing a lot of people say left. I agree. And what makes the left uglier to me is the fraction. Right? The fraction gives me some things that I can do. So I'm definitely going to try that one. All right, so what are we going to do? What do you think? Ideas, thoughts? Well, I know what I want to do. I want to do an algebra step. I want to factor. So if you look at this fraction, the bottom I can't factor. The bottom is just tangent minus 1. But the top I totally can factor. That's a difference of cubes. So hopefully that at least rang a bell in your head and you go, oh yeah, there's that difference of cubes factoring. You may not remember how to do it, but there is a factoring. And the way that that factors, we're going to get tangent of theta minus 1 times tangent squared theta plus tangent of theta plus 1. So if you don't remember that, let me just show you real quick. If you've got a cubed minus b cubed, it factors as a minus b times a squared plus ab plus b squared. And basically, I just put into that form tangent for a and 1 for b, because that's what tangent cubed minus 1 is. It's tangent cubed minus 1 cubed. So that's why you see here tangent minus 1, tangent squared, 1 times tangent, 1 squared. All right, now why was that useful? What good did that factoring do? Okay, so William just said we've got tangent squared plus 1, which we can turn into a secant squared. Good. There's definitely that. Let me go ahead and circle that bit. So we can use the Pythagorean identity to turn those into a secant squared, which is definitely where we're going. All right, and then Adam said we can also reduce the tangent minus 1. Yeah, these factors, I can crack out my red pen, my slashing pen, and cross those things off. So I can cancel those factors. Let me just rewrite it. So this is tangent squared plus tangent plus 1. And then if we use the Pythagorean, we can turn the tangent squared and the 1. We can make that a secant squared. And we definitely have our identity confirmed. So again, this was primarily algebra. There was only one trig step. It was this last one. Turn tangent squared plus 1 into secant squared. All right. So let me switch screens again, just so I can chat with you for a second. Okay, so some reality check here. First of all, I warned you at the start, this is really algebra intensive. There's no way around it. It's also impossible to know which of the algebra you're going to need. It changes. It depends on what they are, right? But I've shown you some examples now of factoring, including difference of cubes, this fraction stuff, taking them apart, putting them together, the foiling. I mean, there's a lot of algebra. So realize that, but don't let it discourage you. Look at this as a chance to practice. And for sure, practice these. You can watch me do these all day long, and it's not going to help you do them. Okay, you need to actually practice them yourself. I liken this to like any kind of athletic event. There's no way I'm going to get good at shooting free throws if I just watch NBA players do it. I won't get good, right? I'll see how they do it, and I might get techniques for, oh, this is maybe how I need to position my body and all that. But until I actually go out there and try it, I'm never going to be able to do it. And this is exactly the same. Okay, you can watch me do it, and I can give you great pointers and techniques, but until you actually get out on that court and try it yourself, you're not going to get good at it. So you have to practice. And at first, it's going to be hard. it's going to suck, right? There are going to be times that you're like, no, I don't want to do any of this. But you got to push through that, right? You have to push through that because this is not going away. And we're going to spend a good month doing identities. Okay. So another F word for algebra. Anyway, so just be patient, work at it, and we'll get there. I will definitely do more examples next time before we develop new identities. But we're going to develop a whole bunch of identities that are going to be useful in lots of places, especially coming up in calculus. You're going to get really tired of me saying this. Oh, just wait for it, just wait for it. But just wait for it. You're going to see where if you can reduce stuff down using trig identities, it's going to make the calculus so much easier. Okay, so I hate giving that answer, but it's the reality here. You'll see it in the future. All right, well, I'm going to go ahead and pause the recording here because I think we're done.